welcome to the Deep Dive. Today we're embarking on a fascinating journey into the world of artificial intelligence. Now you might think AI is all about, clever algorithms and dazzling predictions. And while that's certainly part of it, our deep dive today moves beyond the lab to the true secret sauce, how AI actually works and delivers value in the real world. Think of it like this. You've got this brilliant new recipe, maybe for a revolutionary dish, that got rave reviews in a test kitchen. Our mission isn't just about that recipe, it's about setting up a fully functional, constantly adapting, high-volume restaurant around it. So today we're really unpacking the critical shift from simply building an AI model to constructing a robust, reliable, and maintainable end-to-end AI system. This is where the real magic happens, and surprisingly, it goes far beyond just the accuracy of the model itself.
That's exactly right. And what's truly fascinating here is that the ultimate test of an AI's value isn't its performance in isolation, It's really about its continuous reliability and impact in a live production environment. Companies like Uber and Netflix, they aren't just perfecting algorithms. They're building these comprehensive platforms that manage the entire AI lifecycle. We'll explore why this system-centric approach is absolutely fundamental for anyone aiming to build AI that truly, makes a difference.
Okay, let's unpack this with our first ingredient, data.
Okay.
Our sources are incredibly clear on this. The foundation of any AI system is its data, this data ingestion and preparation phase. It's consistently called the most critical and often the most time-consuming. Why is it so paramount? What's the hidden cost of getting this part wrong?
Well, it really boils down to this. If your data's garbage, your model's going to be garbage. It doesn't matter how clever your algorithms are. The quality of the final AI model is directly dependent on the quality of its input data. Poor, incomplete, or, inconsistent data is the leading cause of model failure in production. It's not just that the model won't perform well, it can actively lead to bad decisions or even financial losses.
That makes perfect sense. Sort of the garbage in, garbage out principle amplified.
Exactly.
So how do these restaurants acquire their raw ingredients, this data? What are the main ways they ingest it?
There's a whole spectrum of strategies, really. It depends on the data source, its volume, and importantly, how quickly you need it. You've got batch ingestion. That's processing data in large scheduled blocks. Think daily reports or historical archives.
Okay, like for background analysis or retraining?
Precisely. Good for model retraining or populating a data warehouse. Relatively simple, but you have higher latency. Then there's real-time and streaming. This is where data is collected continuously as it's generated.
For things needing immediate reaction.
Yes, crucial for fraud detection or live recommendations. Low latency, but the infrastructure is definitely more complex. We also use API integration quite a bit, pulling structured, often high-quality data programmatically from external web services using libraries like requests.
Right, tapping into existing services.
And sometimes, when there's no official API, you might resort to web scraping, extracting data directly from website HTML.
That sounds a bit fragile.
It can be, yeah. Offers flexibility but can break easily if the website changes. Tools like Beautiful Soup help, but it needs maintenance. Finally, accessing cloud storage, data lakes on platforms like Amazon S3 or Google Cloud Storage, that gives you highly scalable and durable access to vast data sets using tools like Bodo 3.
Okay, so a whole toolkit for getting the data in. But once it's ingested, it's rarely ready to go, right?
Yeah.
Our sources highlight what they call the art of data transformation. So once you have these raw ingredients, what does it take to turn them into something usable, something models can actually cook with?
Exactly. Raw data is almost never directly usable by machine learning models. This phase is truly about sculpting the data, revealing hidden patterns. It begins with data cleaning, addressing imperfections, meaning handling missing values. You might remove records or, more often, intelligently fill them in, impute them using the mean or median, perhaps, and also dealing with outliers, those strange data points that can really throw a model off.
Okay, clean up the mess. And once it's clean,
then we move to data transformation and scaling. Many algorithms perform much, much better when numerical features are on a similar scale.
right, so they don't get unduly influenced by large numbers.
Precisely. So you might use normalization or min-max scaling to shrink all values into a fixed range, like 0 to 1. That's common for neural networks. Or standardization, z-score scaling, transforming data to have a mean of 0 and a standard deviation of 1, helps linear models quite a bit. And for skewed data, sometimes a log transformation can make the distribution more symmetrical, more usable for the model.
Okay, that covers numbers. What about data that isn't numerical, like categories?
Good question. You have to tackle non-numerical data too. That's encoding categorical variables. Converting things like country or product category into numbers the model can understand. One hot encoding is common. It creates new binary columns, zeros and ones, making sure the model doesn't accidentally assume some kind of order between categories.
Ah, so France isn't treated as mathematically greater than Germany.
Exactly, whereas label encoding just assigns simple integers like 1, 2, 3. That's fine if there's an inherent order like shirt sizes S, M, L.
That sounds like a lot of careful steps. And then there's advanced feature engineering. This sounds like where the real creative chef work happens.
It really is. This is about creating entirely new, potentially more informative features from the ones you already have. You might do binning or discretization, grouping a continuous variable like age into categories, say A018, 1935, 36 plus,
Right.
or creating interaction features, combining existing features. A classic example is price divided by square footage to get price per session.
Ah, deriving new meaning.
Yeah, even time-based features can be powerful. Extracting day of the week or his weekend from a timestamp can significantly improve predictions in some domains.
Okay, this is fascinating. But here's where it gets really interesting, especially for anyone moving from experimenting with AI to actually deploying it. You mentioned all these intricate pre-processing steps. My sources emphasize that this isn't just a one-off script you run once. Why is that continuity so crucial?
Ah, you've hit on a critical point. That's the silent killer of many AI projects. Training serving skew.
Training serving skew. Explain that.
Okay, so for an AI to make accurate predictions on new data in production, that new data must undergo the exact same transformation steps as the original training data. Any tiny discrepancy, any difference in how a feature is calculated or scaled will silently and often catastrophically degrade the model's performance.
Wow. So it's not just about having the right recipe, using the exact same preparation method every single time.
Perfectly put. It's like having your recipe calibrated for a specific oven temperature, then cooking it in a different one without adjusting. The result will be off, maybe subtly, maybe disastrously. This means your pre-processing workflow isn't just a script. It's a critical, versioned part of a production system, often saved as reusable artifacts using tools like JobLib or Pickle.
Okay, so you save the transformation steps themselves.
Yes, and this concept extends further into governance and versioning. We need to treat data and features almost like code. That means having clear data lineage to track where data came from and how it was transformed, using data version control, DVC tools, to integrate data versioning alongside your code versioning, like Git, and increasingly using feature stores. Think of them as centralized libraries for features.
Feature stores, like a central pantry for prepared ingredients.
Exactly. They ensure consistency. Features are defined, computed, and stored in one place, guaranteeing that both the training process and the live prediction service use the exact same definition and value for a feature, like Uber's Michelangelo platform, for example.
Okay, incredibly important stuff. So we've meticulously prepared our data, those perfect ingredients. Now, how do we build and truly trust the brain of this system, the model itself, the recipe, if you will?
Right. This phase is really an iterative cycle. It's about experimentation, training, and importantly, rigorous validation, choosing the right algorithm. It isn't always about picking the most complex, cutting-edge one. It's often a trade-off, balancing complexity, interpretability, how easily can we understand why it makes a certain prediction computational cost, and of course, performance for your specific problem.
And tracking all those experiments must be key.
Absolutely essential. Systematic experiment tracking using tools like MLflow or Neptune.ai is crucial. You need to log everything: parameters, code versions, native versions, performance metrics. This ensures reproducibility and helps you understand what actually worked and why.
Okay, so you're iterating, training.
Yeah.
How do you ensure the model you develop isn't just good on paper in the lab, but truly performs well in the real world? It's like having a great recipe, but how do you know it will actually taste good when served?
The iterative training and tuning loop is key here. First, data splitting. You have to correctly partition your data into training, validation, and test sets.
Training, validation, test.
Right. The training set is for the model to learn. The validation set is used during development to tune the model and make choices. And the test set, that's your unbiased final exam. It's held out until the very end to give a realistic estimate of performance on unseen data.
Okay.
Then there's hyperparameter tuning. This is optimizing the model settings that aren't learned directly from the data itself, like adjusting the learning rate in a neural network or the number of trees in a random forest. It's like finding the perfect oven temperature and cooking time for your recipe.
How do you find those optimal settings?
Techniques like grid search or randomized search are common. And critically, cross-validation. Instead of relying on just one validation set split, you use techniques like k-fold cross-validation. This involves splitting the training data into multiple folds and training validating the model multiple times. It gives you a more robust estimate of performance and helps prevent your model from overfitting, basically getting too good at predicting on one specific validation set and then failing on new data.
Right, ensuring it generalizes well.
Exactly. Which raises another important question. Why is relying on just a single performance metric, say overall accuracy, so dangerously misleading in AI?
That's a great point. It seems intuitive. Higher accuracy is better, right? But I imagine it's not that simple.
It's absolutely not. A model can achieve, say, 99.9% accuracy but be completely useless.
How so?
Imagine a fraud detection model. If only 0.1% of transactions are fraudulent, a model that simply predicts not fraud for everything will be 99.9% accurate.
Technically correct, but practically worthless.
Precisely. It misses every single instance of fraud. So, we need a multifaceted approach to model evaluation. For classification tasks beyond overall accuracy, we dig into the confusion matrix. This lets us calculate precision and recall.
Precision and recall. Remind us what they measure.
Sure. Precision measures, out of all the times the model predicted positive for email fraud, how many times was it actually correct? High precision is critical when false positives are costly think, wrongly flagging a legitimate email as spam. Recall, on the other hand, measures, out of all the actual positive cases, example, actual fraud transactions, how many did the model correctly identify? High recall is vital when false negatives are costly, like failing to detect a tumor in a medical scan.
Okay, so it's a trade-off depending on the cost of different errors.
Often, yes. And the F1 score is a metric that tries to balance both precision and recall into a single number. For regression tasks where you're predicting a continuous value like price, you'd use metrics like root mean squared error, or MSE, or mean absolute error, MAE, to measure the average magnitude of the prediction errors.
That distinction between precision and recall is so critical. It feels like it defines the success or failure of a model in very practical terms. Are there other hidden biases or blind spots we need to look for?
Absolutely. And this is crucial for responsible AI. We need segment-based evaluation.
Segment-based.
Yeah. Overall metrics, even precision and recall, can mask poor performance on specific subgroups within your data. For example, a facial recognition model might have high overall accuracy but perform terribly for certain demographic groups. Or a loan prediction model might work well overall but poorly for applicants in a specific region.
You need to check performance across different slices of the data.
Exactly. This is vital for uncovering hidden biases and ensuring fairness. It leads to a fundamental difference between testing traditional software and testing AI systems. Traditional software testing focuses mainly on functional correctness. Does the code do what it's supposed to do? But machine learning systems can be functionally correct. The code runs without errors, but logically flawed. They can produce incorrect or biased predictions.
The code works, but the output is wrong or harmful.
Right. So, in addition to standard code tests, AI validation requires automated data validation checks, rigorous model quality validation against performance thresholds, and comprehensive testing for fairness and bias across all those different data segments we talked about. It's a much broader and deeper kind of quality control.
Okay, this is making so much sense. We have a rigorously developed and validated model that we trust. We've perfected the recipe and checked it from all angles. How do we get it out of the lab and into the real world? Into that restaurant kitchen where it can actually start delivering tangible value.
Right, the deployment phase. The first technical step is packaging and serving the model. This usually starts with model serialization.
Serialization, like saving.
Yeah, exactly. Saving the trained model object itself, and critically, its associated pre-processing pipeline to a file, using something like joblib or pickle in Python. This creates a persistent artifact, like bottling your perfect sauce so you can use it later.
Okay, got the model saved, then what?
Then, you typically create a prediction service via REST API. You wrap the model and its loading and pre-processing logic in a lightweight web server like Flask or FastAPI. This exposes an API endpoint. Other services can send it new data, like customer details. The service loads your saved model artifact, applies the saved pre-processing steps to the new data, gets a prediction, and sends the result back.
So it becomes a callable service on the network.
Precisely. And this brings us to a critical best practice, containerization with Docker.
Docker. We hear that a lot. Why is it so important here?
Docker packages your service, the code, the model file, the dependencies, everything into a lightweight, portable, self-sufficient image. This guarantees that your application runs identically regardless of the environment, your laptop, a test server, the production cluster. It utterly eliminates that dreaded, well, it works on my machine problem.
Consistency across environments. Crucial for reliability.
Absolutely. And this containerized approach naturally leads many teams towards a microservices architecture. Your AI prediction service becomes one small independent service. It can be developed, deployed, updated, and scaled independently without messing with other parts of your larger application. Much more manageable.
That makes perfect sense for a single service.
Yeah.
But if our restaurant suddenly needs to serve thousands, maybe millions of customers, how do you manage and scale lots of these containers efficiently in a production environment? One container won't cut it.
Exactly. That's where container orchestration comes in, and Kubernetes has really become the de facto industry standard here.
Kubernetes K8s.
Right. Kubernetes automates the deployment, scaling, and management of containerized applications. It handles things like automatically starting up more containers of your prediction service if traffic spikes, auto-scaling. It manages zero downtime rolling updates when you want to deploy a new version of your model. It can automatically restart containers if they crash, self-healing. It's basically the maitre d' and kitchen manager for your containerized services.
Got it. Orchestrating the whole fleet.
Yeah. And all of this operational machinery is tied together by CI/CD for machine learning, often shortened to MLOps.
CI/CD, continuous integration, continuous delivery. How is it different for ML?
Well, it built on traditional CI/CD, but with some key differences. An ML-specific pipeline might be triggered not just by a code change, but also by a data change, like new training data becoming available.
Interesting. Data triggers the pipeline.
Yes, and the testing stage in an MLOps pipeline is much broader. It includes not just code tests, but also those data validation checks we talked about, and model performance evaluation against specific thresholds. Often it includes a continuous training, CT step, automatically retraining the model on new data as part of the pipeline. And the final artifact that gets deployed isn't just application code, it's typically a versioned model packaged within a containerized API service.
So it's a much more sophisticated pipeline tailored for the ML lifecycle.
Definitely. So what does this all mean for safely launching a new AI, bringing a new dish to the menu, so to speak? Deploying a brand new model directly to 100% of your production traffic is incredibly risky. What if it has a subtle bug or performs poorly on some unseen segment?
Right. You don't want to break the experience for everyone at once.
Exactly. That's why we use advanced deployment patterns to mitigate this risk. One common one is shadow deployment.
Shadow deployment.
Yeah. The new model runs in parallel with the old existing model. It receives a copy of the live production traffic, makes predictions, but crucially, only the old model's predictions are actually served back to users.
So the new model is running silently in the background.
Right. This lets you compare its outputs and performance against the current model on real-world data without any user impact. You can find issues before they affect anyone.
Clever.
What else? Then there's canary deployment, or gradual rollouts. Here, you initially roll out the new model to just a small subset of users, maybe 1% or 5% of traffic. You monitor it closely. If it performs well, you gradually increase the traffic percentage shifted to the new model 10%, 25%, 50%, until it's handling 100%.
So you limit the blast radius if something goes wrong.
Precisely. It minimizes the potential negative impact. And finally, there's A/B testing. This is often seen as a more scientific approach. You serve different model versions simultaneously to distinct, randomly assigned user groups. Group A gets Model 1, Group B gets Model 2. Then you quantitatively measure the impact of each model version on specific business metrics you care about, like click-through rate, conversion rate, etc.
So you get hard data on which model actually drives better business outcomes.
Exactly. It provides statistically valid data on true business value, but it's generally more complex to set up and manage than shadow or canary deployments.
Okay, fantastic overview of getting the model out there safely. So we've successfully deployed our model. Our restaurant is open and serving. Is that the end of the story? Our sources say models are not static. What does that mean? And why is continuous monitoring so vital?
That's a great point. Deploying a model is truly just the beginning of its operational life. It's absolutely not set it and forget it. Models inevitably degrade in performance over time as the real world changes around them. The data patterns they learn during training start to diverge from the live data they see in production.
So the world changes and the model gets stale.
Essentially, yes. This degradation is known as drift. And it's a silent killer for models if you're not watching for it. Imagine your restaurant opens and suddenly your customers' tastes completely change, or the quality of your key ingredients shifts without you noticing. The same dish won't be as good anymore.
Okay, drift. So if the model isn't kept up to date, it's like that restaurant still serving last year's trendy dish when everyone's moved on.
Exactly. And there are two main types of drift to watch for. First, data drift.
Day drift.
This occurs when the statistical properties of the input data flowing into the model in production diverge significantly from the data the model was originally trained on. Think back to that loan application model trained on pre-pandemic economic data. If you deploy it in a post-pandemic world, the input data, like income levels, employment stability, might look very different. The model is seeing patterns it's never learned, like trying to cook with different size measuring cups than the recipe used.
Right, the inputs themselves have changed shape.
Yes. Then there's concept drift. This is often more subtle but more fundamental. It's when the underlying relationship between the input features and the target variable itself actually evolves over time.
The relationship changes. How?
For instance, in a recommendation system, user preferences can shift due to new trends or external events. What constituted a good recommendation 6 months ago might not be true anymore. The very definition of what you're trying to predict, the concept, has changed.
Wow, so how do you even detect this drift?
It's typically detected by continuously monitoring the statistical distributions of the live production data and comparing them against a stable baseline, often the training data or a known good period of production data. Statistical tests, like the Kolmogorov-Smirnov KS test, can help quantify if the distributions have significantly diverged.
So you're constantly comparing new data to the old baseline.
Constantly. And monitoring isn't just about observation. It needs to trigger action. This is where continuous training, CT, becomes a cornerstone of MLOps.
Continuous training, retraining the model.
Yes, CT is the practice of automatically or semi-automatically retraining models to adapt to that changing environment to combat drift. This retraining process can be triggered in several ways, maybe on a fixed schedule, e.g. weekly or monthly, or perhaps more dynamically, triggered specifically by the detection of significant data or concept drift from your monitoring systems.
Or maybe just when performance drops below a certain level.
Exactly. Or when a sufficient amount of new labeled data becomes available, it creates this crucial feedback loop, allowing the AI system to continuously learn from new, live data and maintain its accuracy and relevance over time. Keep the recipe fresh.
That makes so much sense. It's an ongoing cycle. Beyond just the model's predictive performance and drift, what other aspects of the system do we need to monitor for a truly healthy AI? What's on the complete health dashboard for our AI restaurant?
Great question. A comprehensive monitoring strategy really encompasses a hierarchy of metrics. You need eyes on multiple levels. First, yes, model quality metrics. Tracking the model's core predictive performance on live data, F1 score, AUC, ROC, precision, recall, RMSE, whatever is relevant for your task. This often involves joining the model's predictions with the actual outcomes, the ground truth, when that becomes available later.
Okay, basic model performance checks.
Second, data quality metrics. You need to monitor the health of the input data itself. Are you suddenly seeing a spike in missing values? Has the data schema unexpectedly changed? Are values falling outside expected ranges? Poor data quality upstream is often the earliest warning sign of downstream model problems. Tools like Pandera can help define and check these expectations.
Right, check the ingredients before they even get to the model.
Exactly. Third, operational metrics or software health. This is about the performance of the infrastructure serving the model. Things like API latency, how quickly is it responding? Throughput, how many queries per second can it handle? Error rates, are requests failing? And resource utilization, CPU, memory usage, standard software monitoring really, using tools like Prometheus and Grafana.
Keeping the lights on and the service running smoothly.
Precisely. And finally, and arguably most importantly, business KPIs, key performance indicators. Ultimately, an AI model is deployed to achieve some business objective, right? To increase revenue, reduce costs, improve user engagement.
Yeah, it's not just for fun.
Right. So it's absolutely essential to monitor how the model's predictions are actually affecting those key business metrics. For a recommendation engine, that might be click-through rate or conversion rate. For a fraud model, it might be the value of fraudulent transactions prevented. This directly connects the model's technical performance to its actual business value. Sometimes a model can look good on technical metrics but fail to move the needle on business goals or even hurt them.
That closes the loop back to the original purpose. Fantastic. So, thinking about this whole complex system, What does all this mean for an organization deciding how to even start building these end-to-end AI systems? There's a big build versus buy question looming over all of this, isn't there?
Absolutely. It's a major strategic decision. The build versus buy choice for an AI platform, or even components of it, involves significant trade-offs. Building in-house, from scratch, or mostly from open source, offers complete control, maximum customization to your specific needs, and avoids vendor lock-in. You own the IP.
But the downside,
High upfront capital investment, significant ongoing maintenance effort, and you need a dedicated, highly skilled engineering team, data scientists, ML engineers, DevOps, data engineers. The total cost of ownership, TCO, can be high, although it's usually more transparent.
okay, so build gives control but needs serious resources. What about buying?
Buying an off-the-shelf solution, a commercial MLOps platform, for example, generally provides faster time to market, a lower initial investment, and reduced maintenance overhead because the vendor handles a lot of that.
Sounds appealing. The catch.
Limited customization you might have to adapt your workflows to the platform's way of doing things. There are often recurring subscription fees, which can add up, and you face the risk of vendor lock-in, making it hard to switch later.
So faster start, less control, potential lock-in.
Pretty much. In practice, what you see most often is a hybrid approach. Organizations integrate best-of-breed open-source tools with some commercial solutions, leveraging pre-built components where it makes sense, while building and customizing the parts that provide unique business logic or competitive advantage.
Mixing and matching. That makes sense. Now, here's where it gets really interesting. You touched on it there. Regardless of that build versus buy decision, our sources strongly emphasize that open source software is the undeniable foundation of the modern AI ecosystem. Why is it so indispensable? What makes open source such a powerful ingredient for everyone in this space?
Oh, it's absolutely fundamental. Open source is vital for several key reasons. First, it dramatically accelerates innovation. You have global collaboration, thousands of eyes reviewing code, sharing ideas, building on each other's work. Progress happens much faster than any single company could achieve alone.
The power of the crowd.
Exactly. Second, it lowers the barrier to entry. It democratizes access to incredibly powerful AI technologies. Startups, researchers, even individuals can access state-of-the-art tools without massive licensing fees.
Making AI more accessible.
Definitely. Third, it fosters transparency and trust. Because the code is open, the community can scrutinize models and tools for safety, security, fairness, and bias. This is becoming increasingly important for responsible AI development.
You can look under the hood.
You can, and just think about the tools we've mentioned. Major stages of the AI lifecycle rely heavily, often almost entirely, on open source libraries. Data preparation, Pandas, scikit-learn, model development, PyTorch, TensorFlow, Keras, scikit-learn again, deployment, Docker, Kubernetes, monitoring, MLflow, Prometheus, Grafana. It's everywhere.
It really is the bedrock.
It is. Even when an organization buys a commercial AI platform, they are very often purchasing a managed, integrated, and supported version of these fundamental open source components, maybe with some proprietary additions on top. The open source core is almost always there.
What an incredible deep dive. It's so clear now that the path to production-ready AI is really a journey of shifting perspectives, moving away from focusing just on a model's accuracy in isolation to architecting this complete, resilient, automated system around it. It really is about building the whole restaurant, managing the supply chain, the kitchen, the service, not just perfecting one dish in a lab.
That's absolutely right. True success in artificial intelligence isn't achieved the moment a model finishes training. It's measured by the continuous, reliable value it delivers day in, day out in a dynamic, changing production environment. The principles of MLOps, this whole system thinking, provide the necessary framework. It champions automation, iterative development, rigorous holistic monitoring, and collaboration between data science and engineering.
So what does this all mean for you, our listeners? Next time you interact with an AI system, whether it's a recommendation engine suggesting a movie, a fraud detection system protecting your card, or a smart assistant answering your question, maybe take a second. Consider the immense amount of engineering, the constant monitoring, the continuous adaptation that's likely going on behind the scenes, just to keep that service running smoothly, effectively, and reliably for you. It's a testament to some incredible system design.
It truly is. Building a successful AI solution really marries cutting-edge data science with robust, disciplined software engineering practices. It pushes developers and data scientists to move beyond being just model builders, to become true systems engineers who understand and manage the full life cycle end to end. This holistic mindset, understanding the whole pipeline from raw data to production value and back again, is becoming non-negotiable in this field, which makes you wonder, what other areas in technology do you think will increasingly demand such a complete end-to-end view of the system, from initial inputs right through to continuous operation and adaptation in the years to come?